Hello everyone. Firstly, I'd like to thank program coaches for giving me the chance to speak here today. I'll talk about full simulation of fault-tolerant quantum error correction and the general noise for near-time quantum devices. My talk is divided to 4 parts. Firstly, I introduce the backgrounds of quantum error correction, surface code, and numerical results for surface code. Next, I propose a method for full simulation of fault-tolerant quantum error correction. In the third, I'll show the results of this simulation. Finally, I summarize this presentation. In recent years, many researchers have paid extensive efforts for the realization of quantum computers. Quantum computers with over 50 qubits have been developed so far, for example, by Google and IBM. They are now considered as noisy intermediate-scale quantum devices, and their applications are explored. On the other hand, due to existence of noise, noisy intermediate-scale quantum devices are not able to be scaled up. To execute quantum algorithms such as Shor's and Grover's one, it is essential to construct reliable logical qubits, which is protected from noise by quantum error correction. A surface code is a sort of two-dimensional topological codes. With surface code, quantum information is stored in the form of topological order. In surface code, Pauli operations along a trivial loop are regarded as stabilizer, and operations along a non-trivial loop means logical operator. It has a high error threshold, despite that the syndrome measurement for the error correction requires only nearest neighbor 2-qubit gates on a square array of physical qubits. Specifically, the rotated surface code requires to multiply the square of d minus 1 to achieve a code distance d. For example, the required number of qubits with d equal 5 is 49, and hence an experimental realization of one fault-tolerant logical qubit is now within our reach of the state-of-the-art quantum devices. However, it is still challenging to demonstrate that a logical error probability is suppressed sufficiently so that a logical lifetime of quantum information is longer than a coherence time of the physical qubit under a realistic situation. To this end, numerical analyses are indispensable along with experimental effort. Regarding the numerical analysis of quantum error correction, most existing works assume stochastic Pauli errors. The error thresholds are estimated in various noise models, such as code capacity, phenomenological, circuit-level noise models. However, more general noise, including coherent errors, occurs in actual experiments. Numerical analysis for the coherent errors have been done for restricted cases, where the syndrome measurement error is ignored, and the case for the one-dimensional repetition code. In both cases, the error thresholds are smaller than those for the stochastic Pauli errors, and hence it is vital to evaluate an error threshold under the coherent errors. Unfortunately, simulation of the coherent errors cannot be done efficiently in general, and hence it will be challenging to do numerical analysis for fault-tolerant quantum error correction with existing or near-term quantum devices. The number of the physical qubits is 49, and hence a straightforward simulation storing a full state vector requires memory of 8 PB. While it is not impossible for the state-of-the-art supercomputer, for example, Fugak and Summit, it is not so feasible if we think about the number of samples from fourth number of 10 to sixth number of 10, which is required through the simulation. Then, how should we simulate for such a tough situation? From next slides, I show how we solve that problem. To overcome this problem, we had to cleverly design the simulation of syndrome measurements. Specifically, instead of using 24 ancilla qubits to perform a single round syndrome measurement, we reused single measurement qubit to make the qubit behave as virtual 24 measurement qubits. This can reduce the dimension of the state vector, the state vector prepared for a simulation from 49th power of 2 to 26th power of 2, and simulation becomes feasible even on a single node workstation. One sample can be simulated within 8 seconds on GPU, which is NVIDIA Tesla V100. That concept sounds very easy. However, we'll get nothing if the result of simulation differ from a real situation. That circuit transformation does not always preserve the meaning of circuit. In order to these two methods be numerically equivalent to each other, we must carefully choose the order of measurements. Specifically, the order of 2-qubit gate operation on a dead qubit must be equal to the real case. Before thinking about the order of syndrome measurements, I introduce the circuits for measurements. Syndrome measurement is considered of state preparations, single or 2-qubit gates, and measurements. Probabilistic power errors occurs at each operation on dead qubits and measurement qubit. With noises, we unfortunately set measurement qubits to 1 gate. Bit and phase is unhappily flipped through gate operations, and we unluckily get a wrong result of measurement. Furthermore, rotation error, which is coherent, is applied on dead qubits at each step. It is not efficiently simulated by classical computer. When we solve this problem, Tetris is very useful for us. A measurement qubit can be considered to be block in the form of extending its arms from front to back and side to side, like that. The arms mean 2-qubit gate operation between data qubits and measurement qubits. We only can pile on, not insert to, these blocks to place them in lines. That restriction guarantees the order of 2-qubit gate operation on dead qubits. Therefore, the meaning of circuit is preserved. Next, I explain the procedure of numerical experiment. We used Clark's very fast quantum circuit simulator for numerical experiment. First, we prepared stabilizer state of surface code, which logical value is 0. Next, we applied noisy syndrome measurement for 5 rounds. After syndrome measurement, we decoded the logical Z with error detection and error correction. We repeated this experiment 10,000 times for 5 conditions of physical error probability and recorded the logical error probability, which is rate of phenomenon where logical Z flipped from 0 to 1. We considered probability of physical error, state preparation error, single gate and 2-qubit gate error, and measurement error to be equal. Of course, these physical error probabilities are changeable adapt to the real condition. Next, I'll show the results. This graph shows the relationships between physical error probability and logical error probability. Logical error probability is decayed with the nearly third power of physical error probability. On the case where stochastic power errors are occurred on each qubit, it is known that the error rate decays the third power of with the third power of physical error probability. However, the results seem to be more flat than those results are little. It can be explained to the effect of 2-qubit depolarizing errors occur. Finally, I summarize this presentation. Our purpose was implementation of full simulation of 49 qubits fault-tolerant quantum error correction with circuit-level probabilistic power noise and coherent noise. As a result, we succeeded simulating the circuit for 49 qubits related surface code in 8 seconds per a sample with GPU. Furthermore, we confirmed the code suppresses logical error probabilities with the nearly third power of physical error probability, despite of such a circuit transformation. Our future prospect is the investigation, the threshold of the code for the case where real noise happens. Thank you all for listening. Thank you very much.